Gravitational Shockwave, LIGO, detects record-breaking black hole merger. In a discovery that challenges the foundations of black hole formation theory, the LIGO-Virgo KAGRA LVK collaboration has detected the most massive and fastest-spinning binary black hole merger ever observed. The gravitational wave signal, designated GW231123, emerged from the cataclysmic collision of two colossal black holes, weighing in at roughly 100 and 140 solar masses, forming a single behemoth approximately 225 times the mass of our Sun. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video. This gravitational wave event, detected on November 23, 2023 during LVK's fourth observing run, has not only set a new mass record, but also thrown open new questions about how such massive black holes come into existence, especially within the framework of known stellar evolution. A gravitational titan is born. Prior to this, the heaviest black hole merger observed, GW190521, resulted in a remnant of 140 solar masses. In contrast, GW231123 shatters that benchmark by more than 60%, indicating that its progenitor black holes likely formed not from collapsing stars, but possibly through hierarchical mergers, where smaller black holes successively merged to form more massive ones. This is the most massive black hole binary we've seen with gravitational waves, said Dr. Mark Hannum, theoretical astrophysicist at Cardiff University and LVK member. Such objects are difficult to explain through classical stellar processes alone. Their existence suggests a complex, layered history, potentially involving multiple previous mergers in dense stellar environments like globular clusters. Spin to the edge of relativity. Even more extraordinary is the extreme spin of the merging black holes. According to Dr. Charlie Hoy of the University of Portsmouth, these black holes are rotating near the theoretical maximum permitted by Einstein's general relativity. Such rapid rotation complicates both the dynamics of the merger and the modeling of its gravitational wave signal. Accurately deciphering the signal from GW231123 required cutting-edge waveform models that incorporate spin-orbit coupling, precession, and post-merger ring-down physics. As Dr. Gregorio Carullo of the University of Birmingham notes, this is exactly the kind of event that pushes our theoretical frameworks to the edge and forces us to improve them. A challenge to stellar evolution models. Standard stellar evolution theory predicts that stars cannot produce black holes heavier than approximately 65 solar masses due to a process known as pair instability supernovae, which disrupts stars before they can collapse. That makes the approximately 100-140 solar mass progenitors of GW231123 highly unusual. The favored explanation is hierarchical growth in dense stellar environments, where multiple black holes collide and merge repeatedly. However, other possibilities, including exotic physics or primordial black holes, are also under consideration. This event forces us to rethink what we thought we knew about massive star death, black hole formation, and the role of dynamics in star clusters, said Dr. Dave Wrightsey, Executive Director of LIGO at Caltech. Pushing the frontiers of detection, the GW231123 signal pushed the capabilities of the LIGO-Virgo KAGRA detectors to their current limits. The signal was faint and complex with high-frequency modulations from spin effects, said Dr. Sophie Binney, a Caltech postdoc and LVK member. Detecting and interpreting it was a technological and analytical challenge. Gravitational wave detectors like LIGO US, Virgo, Italy, and KAGRA, Japan, operate by measuring minuscule distortions in spacetime, less than 1,000th the width of a proton, caused by distant cosmic cataclysms. Since LIGO's first historic detection in 2015, the network has now observed nearly 300 black hole mergers, but none quite like GW231123, a data treasure trove for the future. The data from GW231123 will be publicly released through the Gravitational Wave Open Science Center, GWOSC, allowing researchers worldwide to reanalyze the signal with evolving models and theories. The discovery will also be highlighted at the 24th International Conference on General Relativity and Gravitation, GR24, and the 16th Eduardo Amaldi Conference on Gravitational Waves in Glasgow, UK, July 2025. This is only the beginning, said Carullo. GW231123 is an astrophysical Rosetta Stone. It may take years to decode, but the insights it offers into the extreme universe are likely to be profound.